Good morning. Bonjour tout le monde. So how is everyone? So last night, I left you with this problem and said you can try it or we'll try it in the morning together. So let's finish this and then do the last document, cover the last document, and then I can answer any questions you have. All right, so we were reminding you, for people who were not here last class, I added in this statement, otherwise you cannot solve this problem like I did. Okay, so I added that statement that the bonds are 20-year par value bonds, and that way I was able to set up this equation and solve for the effective semi-annual rate. Bonjour. So, where we left off was I left you with these two rates, and then I left you to calculate the WACC. And some of you did. So let's write that together. So you need the ratio for stock, which we know is 3/4, 0.75. And then we put in this value, 0.2105, plus the rate for bond is 0.25, or the weight for bonds. And then this is 0.1025. And 1 minus TC. And that is going to give us the WACC. And because it's a linear combination of those two, it will be somewhere between those two. RB, the return to debt, and the return to stock or shareholders. Return on equity. And Harry gives us 17.325. Anybody else find a value? Looks good to me. So I did give you the answer key for this, but you should be able to reproduce the results on your own. So this represents the return to an investor in the firm at the same time as it represents the cost of capital for dollars of financing. Okay. Okay, very good, Luxo. Very good, Francette. All right. So I'll wait for a few more to get it, and then I will go on to the last document. Hi, Kari. The 19.25 is given above at the top on the question paper. You see? Given. Hello, Jean-Baptiste. Very good. The RU is for the shareholder in the all equity firm. So this is a firm with only shareholders. RS is the shareholder in the levered firm, you see, because there's debt. I did have some notes there. Where was that? I made the notes about that here. The different kinds of actors. Did I put it here? No. I guess I put it in the solutions. No, not sure where I put it. Oh, here. No. I made a list of the different characters. And I want to see where I put it. Not here. On the other. No. Not here. So it must be in the notes. Right, so maybe I have to go. It's like this. Okay. There it was. So here I described the different players. In the unlevered firm, there's just the shareholders. In the levered firm, the firm with debt, there are shareholders who get the return RS, bondholders that get the return RB, and the average investor in the firm that is part shareholder, part bondholder in the same proportion as the firm itself, and the firm does its financing. Okay, so those are the different actors. So if I put that in my that's who everybody is. Okay? You're asking me good questions. Clarifications. So levered means that the firm issues debt and then shares the profits with bondholders, and shareholders don't like that necessarily. But what I demonstrated that if the debt results in increasing the value of the firm, shareholders care about that. If it results in decreasing the value of the firm, shareholders care about that. So shareholders are concerned with the overall value of the firm. So they could be willing to take on bondholders if that affects positively the value of the firm. And they are, however, going to demand a higher rate of return because they are less likely to get a share or cut of profits. And the more debt there is, the greater risk of default. And that's what we showed in the end. I introduced the possibility of default. And that means that the firm could risk not paying bondholders. Bondholders could take legal action, take the firm to court, wasting resources, money, and affecting the perception of prospective investors or current investors in the firm, and affecting the share price and the value of the firm. So this can all work against the firm if the debt is too high. And so what we're going to talk about next is, well, there's some benefit of debt, but there's also a cost. So we want to find the optimal level of debt in that case. How is the answer, Harry? Did I answer your question? So we agreed the assignment, the last assignment, you must send to me before Tuesday evening. Okay, very good. Any more questions? Shall we go on to the next exercise? Number document 36. Or 37. 37. What is 36? Oh yes, 36 is the calculus review. I will only refer to that if necessary. But let's see how you do with this review. Capital gains and dividend. Well, if you remember, let's see where we learned about that. That was here. Risk and return. Remember this? Risk and return. So capital gains are So in dollar terms, this is the dividend, so this is the payment made to shareholders in year T, or the end of year T, and this is the capital gain. This is the change in market value. Both are taxed. So if you're a shareholder and you receive a dividend, you have to pay dividend taxes. If you sell the share, then you have to report capital gains from the difference of what you paid for it and what you will sell it for in that year. So that's just that year or that period capital gains. So this is capital gains. In dollars. It's a gain if it's a positive, it's a loss if it's a negative. And this is the dividend here. So we did the exercise here where we calculated the capital gain as a yield, as a percentage. That's different than dollars. So I also presented the idea of capital gains as a percentage. So this is the percentage or yield, capital gains yield, and this is the dividend yield. Percentage is relative to its original price, or the price at the beginning of the year. Any more questions? Or is that clear? So if the price went up, that's a capital gain. If the price went down, that's a capital loss. If you have a capital gain, you have to pay taxes. If you have a capital loss, you save on taxes because that would be considered a cost or loss that you can claim or as a expense, and then that would reduce your taxable income and result in tax savings. That's right. You're right. If the price doesn't change, there is no capital gain. That's right. Keep asking. Good questions. Okay, any more questions? Okay, you ready to go to 37? We can always go back. We'll have time. So we spent yesterday talking about case 1 and case 2, and now I want to talk about case 3, M&M model with corporate taxes and financial distress. Okay, that is case 3 for us. This is document 37. So when you have corporate taxes and financial distress potential, because you've allowed for default risk, and beyond a certain level of debt, financial distress is a very real risk. We assume the M&M model holds and that CAPM is true, and I present to you Protect Corporation. It's a corporation financed with debt and equity. $80 million of its assets are financed by debt, paying an effective annual return of 7%. So what information is that? Can you tell me? There's no one answer, Kathy. You have to take all these things into considerations. That's exactly what we're looking at, is that, well, how do you finance? Well, you'd have to come up with some idea of the trade-offs, and we're just practicing doing that in a modeling type way. So let's pursue this, but basically there's a trade-off that you have to try and figure out, what's happened in the industry, in the related industry, and with everything we've considered, you have to make assumptions and make some estimates. So let's just stick with what's here for now, because I don't think I can make a blanket statement of whether you debt finance or issue stock. I think it depends industry by industry. But these are the considerations you have to make. There is a benefit to issuing debt, but too much debt will signal poorly against the firm, and equity value, shareholders' perception of the value of stock will be affected. And that can impair the ability of the firm to do business as well. Oh, very good. So RB, so what we have here is M. Sorry, M. 80 million is B. And what we have here is RB, and it's given as a effective annual return. So that's how we want it. We want it as an effective annual return. So we've learned a lot to get to this point. When you think about it, we've learned a lot. So we need the effective annual rate. What else? And the remainder with equity. Okay. PCI's earnings are subject to corporate taxes, so TC is 0.4. A financial analyst has estimated that if PCI were all equity, it would have a market value of $500 million. Okay, so this is if it was all equity. So this is the value of the unlevered firm, so no debt. So the value of the unlevered firm is 500 million. And the return on investment in PCI's equity would be 18%. So that represents RU. See, if it's unlevered, it would be 18%. So this is the information I've taken from the case so far. Any questions so far? So allow me to highlight the important elements. This is 80 million by debt, and then 7%, and then the remaining is with equity. So earnings are subject to corporate taxes. So if it's an all-equity firm, its market value would be 500 million, and PCI equity would be 18%. All right. So that's the information. This is case number 3 because taxes and financial distress. So case 3. Good questions. So now we want to calculate the market value of TCI under its leverage capital structure in either case. So I have to do A. Let's do A first. So what is the value? So we know the value if it's unlevered. Now we want to figure out the value if it's levered, if we have added that debt. What equation do I use? Case 3. Let's go back to what I wrote in the notes. So in case 3, where did I summarize everything? I gotta look for my notes. Not here. Must have been in the problem. I know I wrote it somewhere. Did I write it here? No. Sorry, I'm looking for where I wrote it. Oh, let's just write it again then. I'll just write it out again. So case 1, case 2, case 3. So case 1, I'll rewrite it up here. So these are the conclusions, right, of our analysis. Case 1 is where the value of the levered firm doesn't change. And that was only possible given several assumptions, including the that there are no taxes and there's no risk of default. That would make this possible. Otherwise, this is unlikely. So leverage does have an effect. So then we introduce case 2, In case 2, the leveraged firm is equal to the unlevered firm, but we also have the perpetual tax savings when there's taxes but no default risk. And then all those other assumptions as well. But those are what changed. And then case 3, we allowed for default risk. And this is what we're going to use. So this is VU plus TCB, but then it's offset by the present value of financial distress cost. Now, if you could estimate a function, that would be great. We're going to practice with a function, but in reality, it would be a very rough estimation. Thank you, Anouk. Page 8 of document 33. I wrote them down. So this was summarized on page 8 of document 33. All right. So, knowing that we're in case 3, because we've allowed for taxes and risk, default risk, at some point, it's not a good idea to add more debt. It's not a good idea to go beyond a certain point of debt issue. So what I'm going to do is just take this part, together with this information and this question here, and start solving the problem. I got the whole thing. I didn't want the whole thing. I want just this. Oh my goodness. That was very unpredictable. So this is what I want, this information. Okay? And so we make an equation. This. All right, I wanted to do this easy, but okay, so there are the details of the case, and now I have to write up for case 3, VL is equal to BU plus TCB minus present value of costs of financial distress. And this function is an exponential function. Exponential functions, remembering this is just a line, this part with a linear shape, right? But then this part is an exponential function, but it's in negative. So what does an exponential function look like? An exponential function looks like that, or even more like that. But it's a negative in front, so it goes the other way. So it's offsetting. It offsets the linear function. Okay, so these are going to be balanced out against each other, and make basically a concave function. At some point, it's going to turn from up to down. So let's put in all the values. So this is going to be, these are all in millions of dollars, so it's 500 plus 0.480 minus EB30. So let's say we were able to derive a function from data, from information in the industry, for what we've done in the past, using other information. And we want to find the optimal level of debt. So how do we do that? If we have a function that looks like this, then we want to find this. This is the best level of debt for the value of the firm. Now, as students in my other class asked, can they just draw it and then end up here? So I guess if you can put that in Excel and get a drawing, or you have a graphing calculator, but how are you going to find out where is the peak? So we learn the efficient optimization technique of differentiation to solve this. What's differentiation? You should, I'll show you. So here's a curve, but along the curve, each point that hits, that's on the curve, could also be part of a line that sits tangent to the curve. That did not work. Oops. Sorry about that. What I wanted to do, I want to make this bigger. No, can't do that. So these, along this curve, you can imagine that there are points there are infinite amount of points along the curve. And each point could be associated with a line that runs tangent to the curve. So I just illustrate that. I'll just do that with this. And what's happening to the lines is they're getting more flat, right? Ultimately, this is the flattest. This one has a slope of 0. It's a little bit crooked. So we want to find the point that corresponds to this line having a slope of 0. We can find the slope of this line. The slope of this line is known as the derivative. Okay, so what we want to do is find where this function has a derivative of 0. We want to find the b for that situation. So if we take the derivative of the function and set it to 0 and solve for which level of debt makes it so, we have found the optimal level of debt. Okay. So what we do, so I'm going to do this problem and then we'll determine who does not know calculus and who does. But just follow along. Knowing calculus shouldn't limit your understanding of what I'm doing. I mean, not knowing calculus. So the first derivative we go piece by piece. Okay, so the first derivative will be oh, sorry, I have to put this here. Let me change the function in terms of b. Let's do that first. Okay, so this is the function in terms of B. I just exchanged putting 80 in there because what I wanted is a general function of B. So I've made it a general function of B. Okay. E is 2.71. It's a fixed number, exponential. The E. .718. So that's a constant. It actually has more decimals. I just rounded it. And let's say we wanted to get the current level of debt. Let's use the function first for that, and then we'll take the derivative. So the current level, using the current level of debt, find the current value. Okay, so in other words, where B equals 80 million. Notice these are always in millions of dollars. So what you need to do is take the value of the firm and enter 80 million. So this is all in dollars. And what do you find? What's the current value of the firm that's levered? So that's part A. All good. Kenold has an answer for us. Okay, let me specify here, because this 30 is not in millions. It's just 30. So maybe I have to specify this is millions, this is millions, this is millions, and this is millions. I think that I need to do that. Let's see if that's correct. Let me check if it's 30. A few different answers. Okay, so this matters how you enter into the calculator. I'll show you. Just keep trying, and I'll show you in a moment. Okay, the 30 should be treated like a million as well. It's not very clear, but that should be treated like a million. Okay? Everything's in millions of dollars. So this is it's all in millions. I don't have to write it. But so how do I enter this in my calculator is the question. So let's go to the calculator, clear what's here. So I'm going to start at the end. So I'm going to enter 80 divided by 30, that's the exponent, and then I'm hitting second e to the x. Now that is the last term. Put a negative in front and store it in 3. I'm working backwards. And then a 0.4 times 80 I'll store that in 2. And in the first one, I'm going to store 400, store 1. So what I have is the first term, the second term, and the third term. And now I'm going to add them together. Recall 1 plus recall 2 plus recall 3 equals. And that's the answer. All right, Luxo got it. Very good. Okay, Kenold got it. Okay, so just a matter of clearing up what that exactly was here. This needed to be an M on the bottom or it doesn't work, okay? And so your result is also in millions. It's 517 million. And 61 million. Okay, so the thing that I changed was just understanding that this is 30 million here. All right, now, so we found out that at the level of debt of 80 million, the current level of debt, the value of the firm is 517.61 million. Is that too much debt? Could we do better with less debt? Is it too little debt? Could we do better with more debt? That's what we have to figure out next. Any questions? So I gave you information that you had to read and then identified a function for financial distress costs that you had to subtract and create a new function. And then we use the function at the current level of debt for the current value of the firm. We get 517.61 million. So let's see if how will we find the optimal level now? You need to take the function and take the derivative with respect to b. Okay, when you guys are ready, tell me when you're ready. So I'm going to solve this, and then I'm going to show you that this isn't so hard if you don't know what I'm doing, because you didn't learn calculus. So basically, when you take a derivative of a function, you're finding the slope function. And then what you have to do is plug in the point to know exactly which slope you're talking about, because there's infinitely many slopes here along this curve. So notice that when this is like a squared, this is a function that has a, well, I've turned a line into a curve by subtracting this term. So it'll look something like this. This is not exactly the drawing, it's something like this. But when I take the derivative, I get these lines because this is a curve, right? But what if I start with a line? What is the derivative of a line? So let's make some notes. So if you have a curve, like with like just one, like a single curve, not a multiple curve. If you have a single curve function, the derivative will be a series of lines. So or a function of lines, like the green ones that I've highlighted here that maybe you can't see clearly right now. You know I've done this. So it's a series of lines, or I should just say function of lines. Or I should just say a linear function. Let's just say that. But what about the derivative of a line? So what is 500? 500 is, if I just look at like something, v equals 500, v equals 500 is just a straight flat line. So if the derivative of a curve is a line, the derivative of a line is actually the slope of the line if the slope of the line is 0, like this flat function, so let's say this was 500 here, then it's going to have a derivative of 0. So this 500 has a derivative of 0. This is a line, right? So this function, 0.4b, is like a slope. So the function, if you just look at this portion alone, this is a line going through the origin with a slope 0.4. So the derivative is just the slope. And then this function here, to take the derivative, it's not just a single curve. It's, well, I guess it is, but we need to know how to take the derivative of that. In this case, I'm going to be explicit here. If it's a single curve like x squared, it just ends up being 2x. If it's a single curve like 2x squared, it ends up being 4x. Okay, these are just some examples. I'm going to show you my handout in a moment. But I'm just trying to get us there. All right. So this curve turns into a line. This curve turns into a line. This flat line has a slope of 0. That's why I put a 0 here. This, if you just take this portion and see that it's a line, it's the slope of the line is the derivative. And now we have to take the derivative of this. That is not as straightforward as what I've talked about so far. So there are some rules about derivatives. And I've summarized them in this document 36. I actually used this document for my managerial economics course. And if you want to review what a derivative is, I recommend you watch this video. Here's some practice exercises if you really want. I'm not going to do anything elaborate. If I ask you on the final test to differentiate, I'll probably just give you the derivative. I won't ask you to differentiate, but I want you to know how to do what a derivative is, okay? So notice there's different types of rules for different types of functions. So this is the first one here. When you have a constant function, so for example, like we had f of b, right, equals 500. Well, that's just like f of x equals a. There's no variable here, it's just a number. So then the derivative of that, that's the notation, is just 0. Okay, because it's a flat line and there is no, it's a flat line. There is no slope. So the slope is 0, sorry. There's a slope of 0. A line function, the slope of a linear function, well, this part is just going to be 0 from the argument above. And this part, well, the derivative is just the slope. So you end up just getting the slope for the linear function. So far we have the constant function has a derivative of 0. A linear function has a derivative of the slope, just like I said before. When you have a function, so let me use the example. We had fb equals 0.4b. So then here f prime b was 0, and here f prime b is just the slope, 0.4. So you go piece by piece. What about the power function? The power function says that you go down in power. So that's somewhat what happened here with the line function. You can imagine there's a 1 exponent here. And I turned a line just into a constant. So you think of it as going in steps down in power, right? So a constant became 0. A line became a constant. A curve goes 1 power down. And these can all be proven, but these are just the quick rules that everybody remembers when they compute derivatives. So the way it works is, for example, if you had I need to move this one away. Right. So if you had, for example, let's say that was your function. So the derivative of that would be that the exponent, the power, comes in front, but there's already a number there, so it must be multiplied to that number, and then the power comes down by 1. And here we imagine a power 1. You can think of it as a 1 coming in front, and then b raised to the 0. So this becomes a 1, and this becomes 6b plus 1. So this is how we take derivatives. So I need to know if you guys are following, or if you're not. You have to tell me, because I can just give you the derivative, but you still need to know how to use it. You won't have to calculate it per se, but these are the rules that are used to calculate derivatives. So I have so many rules. If you have two functions being added, the derivative of the sum is equal to the sum of the derivatives. Similarly, if they're difference functions. So those are all pretty straightforward if you understand the idea of a derivative and the power function rule, or they call it the chain rule here. This one. Actually, I think it's the power function rule, because the chain rule is a little bit different. The product rule is that if you multiply two functions, you have to take turns calculating the derivative of the first times the second plus the first times the derivative of the second. And then there's a rule for quotients, but I'm not going to give you anything like that. This is just to be comprehensive. I've put these in here. So some of you may have learned about calculus and derivatives before, and this is a reminder. For those people who've never seen it, it's a really nice summary, because what I want to do with this is use the derivative. Notice, okay, so this is the chain rule. Let's say you have a function inside of a function like this one here. So here you have a function inside of a function. Inside you have x squared minus 1, and then it's being squared. To take the derivative of that, you begin with the outside function and you treat it like it's y squared, let's say. So you take the derivative of that, you bring 2 down, and you leave this here, just like you would in the power rule, but now you go inside and take the derivative of the inside part, and that's why you get 2x, because that becomes 2x and that becomes 0. So that's the chain rule. For logarithmic functions, these are interesting. Again, still the same principle applies. We want the slope, we want a function of the slopes of this curve. So this is actually a function of the slopes of this curve. The logarithmic function has a shape like this, and e has a shape like this. This is e to the x. And this is log of x. Anyway, so just to be clear, like this one goes through. These are inverse, these are mirrored functions, e to the x and log of x. So what we are using, so let's just go to what we're using. We're using this function here. Like a version of this one. Because we had e to the b over 30, right? We had e to the b over 30. So the derivative of that is the b in front, and then you just rewrite b over 30. So it doesn't change. Notice this is an interesting function because it itself, its function of slopes is the same thing. So that's pretty interesting. So what we have is a function that I called v of b. So v of b prime, which would be the derivative, would look like that. Oh, I forgot the bottom. That didn't work. It's not b over 30, is it? It's going to be, let's be clear, this is just the constant in front. So I'm going to put a 1. Okay, let me clarify what I just did. So the b here is different than the b here. The b here is the function, the variable. So this is like the x. It's not like the b. The b is a constant. So the constant comes in front, and you just leave this alone. Okay, so that basically I've given you the rules, you just need to know how to apply them. So what's important to remember is we are taking a derivative which is a function of the slopes of the curve. And it turns out that for an exponential function, the function of the slopes is just itself. So that makes it an interesting function. So you can read through those, and for some it will be a review like I said. So what we want to do is find something happened to my curve. This is not it. I think my lines got twisted here. Let me see what happened. Somehow in saving the document got affected. I didn't notice till now. Yeah. I don't know what happened. I'm going to send it again. But okay, so it should be... This is terrible that it did that. So what I'm trying to show you here... Well, let's take 5 minutes and I will take a 5-minute break and I'll send you the clean document. Rather than confusing you. Okay, I sent you the document and here's the corrected graph. Okay, so this is what we're doing. First, we suppose we have a differentiable function. There will be a single, or in other words, the x will generate a global maximum like this, or a global minimum like this. Global meaning only one, other than, a function that maybe goes up and down. This would be the global maximum, right? And this would be a local max. But if there was just one, then it should be where the first derivative is 0. Since the first derivative is the slope of the function, this rule gives us the candidate for maximum or minimum. We don't know which one it is. It could be this one, or it could be a function of a minimum. Now, if you recognize functions and you know their shape, you don't have to worry. But then again, you don't even need to know its shape. You can just use the derivatives to test whether you have this or this situation. We're looking for an optimal debt. So the test to make sure that yours is a maximum, not a minimum, is to take a second derivative, and the second derivative should be negative. Okay, and I usually tell students to remember negative, it's a sad face. And positive is a happy face. Okay, so negative goes down, positive goes up. In this case, we want a maximum. So we want it to go down. And we want the second derivative to be a negative. Okay, if it's not, then what we found is a minimum. And what we're trying to optimize right now is the value of the firm. So I've just made some notes here to remind us what to do. The second derivative of the function is denoted with a double prime symbol. If the first derivative is 0 and the second derivative is negative, then fx, the value at x, is a maximum. And you have a negative or a frown shape. If the derivative is 0 but the second derivative is positive, then you have a minimum, or an up sloping curve. So one is concave and one is convex. That's the other terminology you may have heard. This is concave and this is convex. Stated differently, if the second derivative is positive, the function is at a minimum. I just repeat myself. All right, so these are the steps then. This is what we have to do. We have to calculate the derivative, we have to set it to 0 and solve for the value where it's 0. So then we're going to identify either the peak or the trough, the top or the bottom, the best or the worst, okay? And then what we have to do is calculate the second derivative and plug in the value that we got for the optimal debt and check if we get a positive or negative. Okay, so those are the steps that we're going to carry out. So let's go back to the exercise and do that. So here we are. We left off taking derivative of this function. The derivative of 500 is 0. The derivative of 0.4b is 0.4. And the derivative of this, remember, we looked at this, is just EB over 30, and I put the 30 in front. Now I need to set this to 0 and solve for b. My goodness. It's unpredictable when things get separated. All right. So I've made some more room. So we're going to set this equation. So this is the first derivative equation. Set to 0. And now we want to solve for 30. I want to solve for B, the optimal level of debt. So 0.4 minus EB over 30 divided by 30 is equal to 0, or EB over 30 divided by 30 is equal to 0.4. So that what just happened? And then EB30 is equal to 30 times 0.4. And then so let's simplify this and solve. What do you get? So this becomes the exponent equals log 12. So b must be 30 times log 12. So this is b star. What do you get? So you should have been able to follow everything. In case you don't know derivatives, what I can do is just give you the function, and then you still have to solve and interpret. So you need to learn that. But I don't expect you to actually compute the derivative, but I expect you to use it. So I get 74.55 million. What do you get? So in the exercise that we just did before, part A, it was with $80 million. So $80 million was too much. So this value of B could actually increase the value of the firm. Very good, Anouk. Very good, Francette. Ulrich, great, great, great. All right, so now let's see the value of the firm. Well, let's check first that this is a maximum. To check if this is a maximum, I have to give you the second derivative, right? So allow me to copy this. So what we had was the function for the value of the firm was 500 million. Well, I left out the millions. I converted it all to millions. So 500, 0.4b minus e to the b30. And then we took the first derivative and wrote VL prime. And the first value becomes a 0. This becomes just the slope 0.4, and this becomes itself times its constant. Now let's do a second derivative. So the 0 is just 0. So this becomes these terms disappear, and all we're left is this, and it becomes again itself, again times 130, but then another 1 over 30, EB30. Same rule as before. So this is actually EB30 divided by 900. And what you have to do is recognize, oh, and I forgot the negative. That's the most important thing. I can't forget the negative, because the whole point is that this will be less than 0 for all values of debt. And debt is a positive, so that will always be negative. So we know that this function goes down like this, and we know that the b that we got is a maximum. We only got one, so it's the only maximum. Okay, so now figure out the value of the firm at the optimum. What am I saying? I'm saying take the function and insert. I'm saying take the function and insert the optimal level the original function and find out what's the best value you can achieve. And then we'll figure out what the value of equity is, right? We'll find the value first for the firm, then we can get the equity value. So this would be, oops, I'm going to put 74.55 in there. And then minus e to the 74.55 divided by 30. Let me erase this line. So this would be the optimal value of the firm. What do you find? If you have difficulty with equations, try and use an Excel maybe to keep things in order. Okay, I'm going to be more precise with my B star. Oh, I am more precise with the B star in the solutions, but let's just leave it like this for now, just to make it a little easier to enter. So what do you get? Very good. So this is 517. So the number looks familiar. 517.82 million. And we had before with 80, the value of the firm was equal to also 517, but just a little bit smaller, right? So the best we can do is 517.82 million. It was 61 before. So we shot the optimum by going for 80 million in the first part, but then here we found the optimum, so just a little bit less debt, and we have a greater value. So the last question is, what would be the value of equity? And I'm going to put that as at B star. So now you would take the value of the firm at B star minus B star, and that will give you the answer. So it's 517.82 minus B star, which is 74.55. And you can get the value of equity. I have all the decimals in the solutions, but for this, so the value of outstanding stock is 443.27. All right, so we've learned that in an extreme case, we can show where value of the firm is not affected by debt. But it's so extreme that it's likely never to be the case. So we understand that debt has an effect on the value of the firm that the shareholder cares about, because the shareholder cares directly, or is directly impacted by the value of the firm. If the firm does well, so do shareholders. If the firm does poorly, so do shareholders, right? So they care about the overall value of the firm. So they are willing to take on debt provided the benefits outweigh the costs. So financial distress, if there's a risk of financial distress due to a risk of default and too much debt, shareholders will dislike debt or any additional debt. Okay, so this tempers the equation of the case 2, and we see that we can find an optimal level of debt, at least in this situation. And we can calculate the optimal debt here, and the optimal value of the firm, and the optimal shareholder equity. So let's do the second problem. Are you ready? The second exercise, a different function, fresh start. All right, let's try the second question. The second case is a function 2 log b. And it's also an increasing function, so, right, because I said exponential functions look like this, and logarithmic functions go like this, and they are mirrored through the identity line here. So they're both increasing functions. And if I put a minus in front of them, they will both be decreasing functions. Sure. Monsieur Sever, you have the solutions I sent you the solutions to this exercise. You already have the document, but it's fine. It's easier to recall this because you've seen it demonstrated, so I understand taking a screenshot. So calculus, if you can derive a function that's suitable, calculus can be very powerful as a tool in optimization. Yes, yeah, you'll be more likely to remember this copy. All right. And let's go back to the second question. So in this problem, we have the function is 2 log b for financial distress. So let's take the information with us. Let's take this now. And we still need the other information. All right. So we're going to repeat what we did, but now with this function. So we begin with the value of the levered firm is the unlevered firm plus TCB minus 2 log B, right, from case 3. So I'll put that information there. I'll move this up here. And what we have to do is first, let's find out what the current value is at 80 million. B equals 80 million. Very good. 523. So we have 523.24 million. So that's the value. It's more, right? This function has a greater value, gives a greater value estimate for the firm. Now, we want to find optimum you want to find B star, the optimal level of debt. So what we do is we take the first derivative of the function. Okay, so I treat this like a function. This is going to be the same as before. The derivative of a constant is just a flat line. The slope is 0, so that's 0. The derivative of a line is just its slope. And the derivative of this function, well, if we look at let's look here at our functions, and we did see the logarithmic function here. So the derivative of a log is the inverse function. The derivative of a log with a constant in front is just the inverse function, leaving the constant there. And let's copy that over. So what we have to do is take the sine, and the answer is just 2 over b. That's the derivative. Okay? The next step is to set the derivative to 0 to find where are we. So the derivative is the function of slopes of the line, but I need to find the slope, the position where the slope is 0. So I set it to 0, and I get 0.4 minus 2b, and then I can solve for this. So this tells me that b must be and we always interpret these as millions, so this is 5 million. Wow, that's it? 5 million. Okay. A lot less debt. Did I do this correctly? Let me see. Yep, you got 5. All right. So that looks correct. Let me check this number because now I'm a little bit unsure. Let me double check that number. Oh, it looks like it's right. 5 million. All right. So what have we found? It's very bizarre, right? Because we started out with 80, and this is only 5. So maybe something else is going on that we have to verify. That this function is actually not concave. So let me show you what I mean. If we plug this in, so now let's say this is the optimum. This is optimal, but we need to verify if it is a max or a minimum. We don't know that yet, and it looks like it's probably a minimum. So you got to be careful and make sure you check. So what we're going to do first is I will plug it in to VL, the original, to see what is the supposed optimal value. So that would be putting it back into the original expression, 5 million minus 2 log 5. And you're going to see that you get a number smaller than 523 that we got up here. So that tells you that you found a minimum, not a maximum. What do you get? Okay, Francais, let me plug it in for you, okay? So let me show you how you enter that value. So we want to enter, what I'm going to do is put these in storage. I'm going to put 500 into store 1, and then the second piece is 0.4 times 80, and that goes into store 2. And the last piece is 80 log times 2. And then I make a negative in front and store 3. Now I just take the amounts and I recall 1 plus recall 2 plus recall 3. And I get 523.24. Now, when b is equal to 5, what do you get? I get 498.78, and this will be in millions because everything was in millions. So this ends up being smaller than what we started with. So clearly our optimum is not a maximum, it's a minimum. And I'll show you, using the derivatives, I'll show you how we can see that. Very good, Harry. So what I'm going to do is take, so I'm going to write the first derivative down again, and then we take the second derivative. The derivative of a constant is 0, and the derivative of an inverse function is like a power function. You should see this as the power function. Let me grab that from the list of functions here. So what this says is, if you have a function with a power, that comes down as a constant in front, and you reduce the power by 1. That's the derivative. Let me make it a little bigger. So what about 2 to the b minus 1 if that's a function? If that's a function, then it would be 2 negative 1 b to the negative 2. That would be the application of the power function. And that reduces to negative 2b negative 2. So this would be like that. So the second derivative, notice, is going to be a positive. This is always going to be positive for all values of b. So what does it mean? It means that the function is not concave. It's a convex function. This got twisted. So our function actually looks not like this. It goes like this. The second derivative is positive. And we found a minimum value. So actually, the 5 million gives the lowest value of the firm. So what would be the answer here? This function is going to go higher and higher and higher. The value is going to increase unbounded as long as you increase debt. So in this example, you can have as much debt, just infinite debt is the answer. That's the optimal level. So I don't want you to get confused with the calculus. The calculus is a tool, all right? It's the interpretation that really matters. So the answer to the question is there an optimal amount of debt for this function? The optimal debt is infinite. Now, is that realistic? Well, the function that we use probably is not realistic, but if that was the function, that would be the answer. The optimal level of debt is infinite debt. Any questions? So B star would be equal to infinity, and VL B star would be equal to infinity. And because that's not realistic, it probably there's probably something wrong with the formula, okay? But that's the result. So that is that. That's all I wanted to show you. So, do you have any questions for me? So you should be able to identify which case you're dealing with, case 1, with the assumptions, Modigliani-Miller, no taxes, no default risk. In that case, with all the assumptions, the value of the firm will not be affected by debt. But we know that's not realistic, and we begin to remove some of the assumptions, and we bring in the reality of taxes and see that there's the incentive for the firm to issue debt because debt produces tax savings, and it is an unbounded result that the best level of debt is 100% or infinite debt, so that the value of the firm can grow infinitely. That's case 2. In case 3, we temper that result and say, well, wait, we're going to reintroduce the risk of default because that's much more realistic, and create these functions that we can use to determine an optimal level of debt. How do you find that function? Well, you look at past performance. You look at past performance, you look at debt, and you look at the value of the firm. You see how it affects things. Okay, now I'm using pretty nice and tidy. Most of the theory I teach you, things are very tidy in their function. The better you are at mathematic and quantitative methods, the better you are at estimating such functions. Okay? So you would have to, you get industry data, you get your own data on how your firm is performing. In terms of debt, what is the value? In terms of debt, what is the shareholder equity? Oh, we didn't figure that out here because, well, I guess debt is infinite, so shareholder equity would be 0. Right? It should be all infinite debt. There's no room for shareholders. So these functions are determined by regression with data. So with regression, you know, you have historical data and say this was debt and the value of the firm historically, and you try and find the function. So here, the way I've drawn it, it's a line, right? But maybe so the importance of statistics cannot be emphasized enough. Obviously, if you have a small firm, you're not going to do things like this with, or a new firm with no information. But the idea stands that issuing debt has an effect, a positive effect, but you have to consider the costs, and that's the takeaway here. You have to consider the benefits against the costs. If you can generate a function that gives you that information, then you can exploit the function to find an optimum. So who knows if the function is like that or like that based on historical data. Or industry data. You could look at other companies that are also public, and you can get information on their debt issue over time, and the value of the firm as the value of assets, equity, and debt. These estimations are possible for publicly traded firms. Not easy, but it's possible. So firm valuation is very important for mergers and acquisitions, very important when one firm wants to buy another one. Valuations like these are part of the negotiation. So what I can do, if you have more questions for me after you work with Taylor this week, I can give you office hours. You have classes though on Friday and Saturday. You just let me know if you have questions. Or I'm trying to think, maybe when you meet with Taylor on Thursday, I can be available. When do you work with Taylor on Thursday? If you need me, you have Taylor. So let me know in advance, and I'll set up a Teams meeting or some way we can talk, or even in WhatsApp, to ask your questions, because maybe there's older material that you still have questions about. So if you don't have any more questions for me, I will have to say goodbye. And I really enjoy teaching you. I know it can be frustrating to be at distance. And even if I was there, I assure you, you would still be stressed because this is a lot of material to do in a month. But I commend you for your devotion and commitment. And I know this is an intense year for you. And I'm hoping that I was able to convey to you what it is you need to know to feel somewhat confident about finance, or more knowledgeable at least. I haven't heard from the administrators in Auvergne, so we will just have to communicate online about it. I will definitely let you know, okay? I'll be in touch with the email about how the test will be. I haven't had a chance to see if I can just put it online with multiple choice. I think I might use the Comunidad platform that we use for statistics. I have to check if you're still enrolled. I'll let you know, Luke, so I have to make sure it works. Harry, you want more exercises? You sure? I gave you a lot that we did together. Or you want me to put them on the platform to practice? Thank you, everyone. I will be in touch about the test. Harry, sorry, do you want that on the platform or by email? For me to type questions into the platform, I'm not going to be able to do it anytime soon. This is the problem. I will do it for the test, but not for other questions. So I don't know if I have any more problems. I'm trying to think if I have more sample problems. I don't think I have any more, Harry, but if I do, I will share them, okay? I'll let you know, Jeff's son, what is happening. I want it to be a 3-hour test, not 2 days, so it should be online. You know, I could probably just set it up in a Google form, now that I think of it. I can do that too. It just won't be you won't get a grade. unless I set it up in the UPR platform. Okay, I'll remember that, Harry. Thank you, Francette. I enjoyed teaching you. I enjoyed communicating, even though it's remote and limited. Yeah, I will let you know about, if it's in Comunidad, I can make it a little longer than 2 hours. The 2-hour limit was for in the classroom to keep you under 2 hours and less exposed. But we will be in touch about the details, okay? Thank you for your insights and input, and I will keep it all in mind. Thank you, Ulrich, Samper. Thank you, Ironel, Marcel Savar. Who else do I have? Jeffson, Luxo, Kenold. I talked to many of you, maybe not all 30. Anouk. Thank you all. Have a good weekend. They're celebrating Mother's Day here. Are you celebrating there? Alex, you're welcome. The 30th. Okay, good to know. Good to know. Interesting. 30th is your Mother's Day. In North America or in Canada, United States, Puerto Rico, they have it on second Sunday of the month. Thank you, Samuel. Okay, I'm going to say bye. I'll stay here if you have questions. I will have, I'll turn my mic off. If you have any more questions, put it in the chat. I'll stay on a minute or so. Bye for now.